Right now, on the Bishoftu Plateau in Ethiopia, thousands of heavy bulldozers and trucks are working non-stop, creating one of the busiest heavy machinery construction sites on the planet. All 35 square kilometers of natural mountainous terrain are being completely leveled, turning the undulating elevations into an absolutely flat construction base. This massive mechanical intervention is the starting point to build a new aviation infrastructure complex with a total investment of $12.5 billion. When completed, the project will feature 4 independently operating runways, capable of handling up to 110 million passengers per year. However, to build a giant transit hub on this plateau terrain, engineers must solve extremely harsh physical barriers. How to compact millions of cubic blocks of landfill and eliminate the foundation settlement? At the same time, how to overcome the reduction of aerodynamic lift when aircraft take off in a thin air environment at an altitude of 1,900 meters. Let's break down the technical details of the Bishoftu Airport megaproject in today's video. If you are passionate about infrastructure analysis and find this video useful, don't forget to hit like and subscribe to continue following in-depth content. Now, let's get started. On the global aviation traffic map, Africa is witnessing a breakthrough in transit volume. From 2025 to 2026, aviation capacity on this continent surged by 6.7%, far exceeding the global average growth rate of 1%. However, the entire logistics network of this massive region lacks a true superhub, a core transit station. In the capital of Ethiopia, the current Bishoftu International Airport has to bear the transit pressure of over 20 million passengers per year. This infrastructure has reached its physical breaking point and is completely unable to upgrade its operational capacity. The core reason is that Bishoftu Airport is nestled right in the middle of an urban center. Its runway and terminal systems are completely surrounded by civilian buildings. Clearing thousands of concrete structures to expand the area on the spot is an impossible problem in terms of geographical space. To completely resolve this bottleneck, the Ethiopian government has activated a major planning solution. That is to abandon upgrading the old facility, move the entire aviation center out of the capital, and head down to the Bishoftu highland area, located 35 kilometers away. This lightly populated area provides a massive empty land space of up to 35 square kilometers. This surface area is larger than both the UK's Heathrow and the US's JFK airports combined. This is the perfect physical space for Ethiopia to establish a completely new aviation mega infrastructure from scratch. Although completely resolving the space barrier, setting up this entire infrastructure complex on the Bishoftu highland, which has an altitude of 1,900 meters, puts the construction force in front of a series of strict physical and earth engineering problems. The first and most vital problem is the reduction in aerodynamic lift. At an altitude of 1,900 meters above sea level, the air density is significantly thinner. The physical consequence is that the volume of airflow passing through the airplane's wings is reduced. At the same time, the low oxygen level causes the combustion chambers of jet engines to suffer a direct drop in power generation efficiency. To make up for this shortage, airplanes are forced to travel at much higher ground speeds to achieve enough air pressure to take off. The only technical solution is to extend the runway system. The 4 runways at Bishoftu are designed with lengths exceeding the 4,000 meters mark. This distance provides enough takeoff distance for heavy superjets like the Airbus A380 or Boeing 777. Besides the runway infrastructure, the next physical problem is optimizing the mechanical movement flow for 110 million passengers. The central terminal complex is assigned to Zaha Hadid Architects for design with a planned size twice as large as the new Manila International Terminal. This giant structure is designed with a central spatial axis branching directly out to the departure gates. This geometric structure completely solves the physical foot traffic problem, greatly reducing the walking distance for passengers. This calculation is required because, according to operating numbers, 80% of passenger traffic will not leave the terminal, but will continue with their connecting flights. However, when a machine weighing over 400 tons lands at a speed of 250 kilometers per hour, it will create a massive physical impact force and stress directly hitting the ground. If the foundation surface has any empty gaps, localized uneven sinking will immediately occur, tearing apart the concrete structure. To support this entire massive architectural block and runway system, a deep foundation reinforcement process is activated. This process is a combination of mechanical intervention steps aimed at completely transforming the physical properties of the natural soil. Stage 1. Mechanical strata stripping. A system of heavy-duty bulldozers and scrapers is mobilized to completely peel off the entire top layer of organic soil. This soil layer contains many impurities. If kept, they will rot over time, creating underground empty spaces and causing uncontrollable foundation sinking. Stage 2. Deep reinforced concrete board piles. At the core location of the central terminal complex and air traffic control tower, the resting weight is massive. The large diameter board pile solution is activated. Heavy mechanical board pile drilling machines with spiral drill bits are brought in to punch straight into the ground, piercing through geological layers to a depth of tens of meters. Right after giant steel cages are lowered into the drilled holes by cranes, thousands of cubic meters of high-grade concrete will be continuously pumped down to the very bottom of the pit. This board pile system acts like solid concrete roots planted firmly into the bedrock layer, ensuring the terminal structure does not shift even 1 millimeter under any shaking. Stage 3. Runway firming with water drains. To eliminate water in the underground mud pockets beneath the runway strip, hydraulic machines will drive tens of thousands of plastic drain strips 20 meters deep into the ground. When the surface is pressed down, the water pressure inside the soil structure increases suddenly. Groundwater, unable to escape sideways, will be forced to run backward up through the drain tubes. This mechanical solution forces the ground to sink to its maximum limit in just a few months, instead of taking decades to firm up naturally according to physical math. Stage 4. Deep soil mixing. At the aircraft parking areas, the ground must have an extremely large resistance force. The construction crew uses multi-axis drill rigs to pierce through the ground. As the mechanical cutting blades chop up the natural soil, the drill bits simultaneously pump cement liquid under super strong pressure directly into the mixing hole. The cement particles immediately react with water, chemically bonding with the clay structure, creating a solid underground pile network that bears direct heavy weights. Stage 5. Dynamic compaction and static foundation pressing. For sandy foundation areas, 100-ton crawler cranes will directly join the battle. They lift solid steel weights weighing 30 tons, dropping them in free fall from a height of 25 meters. The massive impact energy from the strike creates shock waves, sending heavy pressure deep into the ground.